You think Megalodon was the most terrifying thing to ever live in the ocean. Every movie, every documentary, it gets the top spot. But Megalodon would have lost. Badly. Creatures existed that make it look like prey. A whale with teeth the length of your forearm. A fish whose jaws moved faster than your eye can follow. A sea monster longer than a blue whale. We're going to meet all of them. If you enjoy the ride, subscribe and leave a like. Prepare yourself. We begin. Everyone pictures Megalodon the same way. A shark the size of a building, with a mouth you could park a truck inside, cruising through the ocean like a moving wall of teeth. That image is everywhere. Movies, games, documentaries, and it is wrong in almost every detail. Here is what the fossil record actually shows. Megalodon was a real animal. It was enormous. The largest individuals grew to around 60 feet long, roughly the length of 2 school buses parked bumper to bumper. Its teeth reached 7 inches tall, bigger than your hand from wrist to fingertip. Its bite force was stronger than anything alive today. These are real facts confirmed by real fossils found on every continent except Antarctica. But the way people picture the body is off. Movies show Megalodon as basically a giant great white shark. Blocky head, huge dorsal fin, the same silhouette just scaled up. Scientists do not actually know what Megalodon looked like beyond its teeth and vertebrae. Sharks are made mostly of cartilage, which rots away. What we have are teeth and a handful of spine segments. Everything else is a reconstruction built from math and comparison. Early estimates of Megalodon's size used great white sharks as the model. Scientists measured tooth size, compared it to great white proportions, and scaled up. That gave the 60-foot figure. But some researchers think Megalodon may have been shaped more like a whale shark, with a wider, rounder body and a blunter snout. That would make it heavier and slower, less like a speed predator, and more like a giant ambush machine. The weight estimates are staggering. A 60-foot Megalodon probably weighed somewhere around 100,000 pounds. That is roughly the same as a fully loaded Boeing 747 airplane. Picture that. A living animal, in the ocean, weighing as much as a jumbo jet. Now think about what that means for hunting. An animal that size needs enormous amounts of food. Scientists estimate Megalodon had to eat tens of thousands of pounds of meat per week, just to keep moving. That is why it targeted whales. Small fish would not cover it. Megalodon needed prey the size of a car or bigger every few days. Fossil whale bones from the Megalodon era show something chilling. Huge bite marks, circular punctures that match Megalodon's tooth spacing exactly. Some bones show evidence of repeated attacks, suggesting Megalodon bit into prey, pulled back, and struck again. Scientists found whale bones in South Carolina with those marks still carved into them, sitting in museum drawers, waiting for someone to look closely enough. Here is where it gets strange. Megalodon did not just bite and shake the way great white sharks do. Evidence suggests it targeted the hard, bony parts of its prey first. The ribs, the shoulders, the skull. Scientists believe it was trying to crush through the bone to reach vital organs quickly, ending the fight fast. For prey as large as a whale, that was the only strategy that worked. So Megalodon was real, enormous, terrifying, and far more sophisticated as a hunter than most people assume. The movie version is a shadow of the real thing. But here is the part the movies always skip. Megalodon shared the ocean. It was not the only giant, and some of what lived alongside it hunted Megalodon right back. A single tooth washed up on a beach in North Carolina in the 1800s. A farmer picked it up, turned it over in his hands, and had no idea he was holding the calling card of the largest predatory fish that ever lived. That tooth ended up in a collection. Decades later, a scientist looked at it and realized something extraordinary. The size of a single tooth could tell you the size of the whole animal. That is the entire foundation of prehistoric predator science. You almost never find a complete skeleton. What you find are pieces, teeth, because they are made of hard enamel and survive millions of years in rock, vertebrae, because they are dense enough to fossilize under the right conditions, occasionally a partial skull. From those fragments, scientists have to reconstruct animals the size of school buses. The method for sharks is called the jaw ratio technique. A shark's tooth size is proportional to the width of its jaw. The jaw width is proportional to the body length. So if you have one tooth and you know the species, you can estimate the animal's total length with reasonable accuracy. Scientists cross-check this by measuring the same ratios in living sharks, confirming the math works, then applying it backward in time. For Megalodon specifically, the biggest teeth ever found measure around 7 inches. Using the jaw ratio formula and comparing to great white shark proportions, scientists arrived at the 60-foot estimate. A different research team used a different comparison species and got a slightly lower number, around 50 feet. The debate is still active. The honest answer is that we know Megalodon was massive, and the exact maximum size has an error margin of several feet in either direction. Vertebrae add another layer of data. Megalodon vertebrae found in Belgium in the 1800s measured nearly 6 inches across, some of the largest shark vertebrae ever discovered. The largest individual vertebrae suggest an animal even bigger than the teeth alone would indicate. Piecing those two data sources together gives scientists a size range, and they pick the middle of that range as their best estimate. For non-shark creatures, the method changes. With animals that had bone skeletons like the great ancient sea reptiles, scientists use limb bones and skull fragments. A skull length can predict body length. A flipper bone can indicate total size. Scientists measure the same bones in living relatives and build equations. Those equations get applied to the fossil fragments. The problem is relatives. Some extinct predators have no close living relatives at all. Their body plans vanished completely. When that happens, scientists use multiple independent methods, compare the results, and report a range instead of a single number. That range is often enormous. Some prehistoric predators have size estimates that vary by 30% between different research teams. There is also a selection bias built into the fossil record. The animals most likely to fossilize are the ones that sank to the bottom of a quiet sea and got buried in sediment before they could decompose. Active predators in open water almost never fossilize. What we find is a fraction of what existed, and probably skewed toward the individuals that died in unusual circumstances. The largest animal ever might be sitting undiscovered in rock somewhere right now. That uncertainty is both frustrating and thrilling. Every new fossil has the potential to rewrite the size charts entirely, and one fossil found in the last 20 years did exactly that. 50 million years ago, the ocean did not look the way it does today. The continents were in different positions, the water was warmer, the currents moved differently, and the creatures living in it were so strange that if you dropped a scuba diver into that sea, they would not recognize a single animal they saw. This was the Eocene epoch, the age of early whales, the age of sea monsters that science is still piecing together. The ocean during this period was a layered killing machine, with different predators dominating different depths, different regions, and different prey. The water temperature matters enormously. Warm water holds less oxygen, but supports faster metabolism in cold-blooded creatures. 50 million years ago, the oceans near the equator were significantly warmer than they are today. Some shallow tropical seas reach temperatures close to 100 degrees Fahrenheit, approaching the upper limit of what most marine life can tolerate. Deeper water stayed cooler, and that temperature gradient created distinct zones with entirely different predator communities. The shallow seas of this era teemed with early whale species that look almost nothing like modern whales. Pachycetus, one of the first, was a four-legged land animal about the size of a large dog that waded into rivers to catch fish. Its descendants over millions of years got longer, lost their back legs, and pushed further into the sea. By 50 million years ago, some of those descendants had grown to terrifying sizes and gone fully aquatic. The transition from land animal to ocean giant happened in less than 15 million years, which in evolutionary terms is extraordinarily fast. Alongside the early whales lived enormous sea turtles with shells 10 feet across, flightless birds that could swim faster than a modern dolphin, schools of bony fish 20 feet long, and cutting through all of it, Sharks that were already ancient by this point, carrying hundreds of millions of years of evolution in their body plan. The competition between species during this era drove an arms race. When prey gets bigger, predators have to get bigger to hunt it. When one predator species dominates, other predators either find different prey or die out. The Eocene ocean was a pressure cooker for size. Animals grew larger because larger animals survived longer, ate more, and produced more offspring. The ones that stayed small got eaten. This is the environment that eventually produced Megalodon. Millions of years of escalating size, escalating prey, and escalating predator power in a warm, rich, crowded ocean. Megalodon did not appear out of nowhere. It was the end product of a long chain of increasingly massive hunters. But Megalodon came relatively late. By the time it appeared, the ocean had already hosted things that might have made even it cautious. One of those things was a whale with real teeth. Teeth the size of wine bottles. A whale that hunted other whales the way a wolf hunts deer, and it lived in the same waters as Megalodon at the same time. In 2008, a fossil hunter working a dry desert in southern Peru reached into a layer of ancient rock and pulled out something that stopped the entire scientific community cold. A tooth, 14 inches long, thick as a man's fist, serrated along the edges. The tooth of a predator so large and so aggressive that when scientists eventually named it, they chose the Hebrew word for a sea monster from ancient mythology. They called it Leviathan Melville, named partly for the biblical sea beast, partly for Herman Melville, who wrote Moby Dick. The name was deliberate. This animal earned it. The skull alone measured 10 feet long. That is taller than most garage doors. From snout to tail, Leviathan stretched somewhere between 45 and 60 feet, putting it in the same size range as Megalodon. But the body plan was completely different. Leviathan was a whale, built for sustained speed and deep diving, with a massive brain and the kind of social intelligence that modern sperm whales still carry. It probably hunted in organized groups. It probably communicated with sound. And it had the largest teeth of any animal known to science, teeth designed for one specific purpose: biting through the skull of another whale. Modern sperm whales have teeth only in their lower jaw, and those teeth are thin and pointed, good for gripping slippery squid. Leviathan had enormous functional teeth in both jaws, upper and lower, interlocking like a trap. When that mouth closed on something, there was no pulling free. The prey it targeted were other whales, medium-sized whales that shared the Miocene ocean, creatures anywhere from 15 to 30 feet long. Leviathan likely ambushed them from below, the way orcas today ram into blue whale calves, driving them to the surface and exhausting them before the killing bite. The difference is that Leviathan did not need a group attack to finish the job. One bite to the skull with those 14-inch teeth and the hunt was over. Scientists found more material around the original Peru site over the following years, enough to piece together a reasonable picture of the skull and jaw structure. What they could not find was a complete spine or flipper bones, so the exact body length is still debated. But the skull dimensions alone push the size estimates above 50 feet confidently. Here is what makes Leviathan genuinely different from every other giant predator in this list. It was warm-blooded. It breathed air. It probably had emotions in the way modern whales do, because modern sperm whales show grief, play, and strong social bonds. Leviathan was not a cold killing machine running on instinct alone. It was a highly intelligent, warm-blooded apex predator with jaws that could close on a car and teeth that could punch through steel. And it lived at the same time and in the same ocean as Megalodon. Two animals of roughly equal size, both targeting the same whales, both competing for the same food in the same warm Miocene sea. That overlap raises a question scientists are still arguing about. The same fossil site in Peru that gave us Leviathan also gave us Megalodon teeth, sitting in the same rock layer, deposited in the same ancient sea. Two of the largest predators in Earth's history, sharing the same hunting ground at the same moment in time, roughly 12 million years ago. That fact alone should give you pause. Imagine the modern ocean suddenly having two apex predators the size of a semi-truck, both targeting the same whales, both fast enough to run down large prey, both intelligent enough to hunt efficiently. The ecosystem pressure would be immense. Scientists believe the Miocene ocean around what is now the South American coast was extraordinarily rich in prey. Cold upwellings from the deep ocean pushed nutrients to the surface, feeding massive schools of fish, which fed the whales, which fed both Megalodon and Leviathan. The food supply was large enough to support both giants. Think of it like two different wolf packs hunting the same valley, but rarely crossing into each other's exact territory, because the deer population is large enough that they do not need to, but competition still shapes behaviour. If Leviathan was primarily targeting medium-sized whales with its crushing bite, and Megalodon was primarily targeting large whales, by going for their bones and vital organs, the two animals may have settled into slightly different hunting niches. Same prey pool, different strategies, different sized targets. That kind of niche separation allows two apex predators to coexist without constant direct conflict. Direct conflict probably happened anyway. Scientists found bones from this period showing marks that appear to come from both types of predators on the same carcass. Whether that means they fought over kills or simply fed on the same carcass at different times is impossible to say. But the marks are there. There is another angle worth thinking about. Leviathan was a whale. Whales are air breathers. They have to surface every few minutes. Megalodon was a fish and could stay underwater indefinitely. If the two ever did compete directly for a kill, Megalodon had a patience advantage. It could circle and wait while Leviathan had to surface. Whether that ever played out as a real hunting strategy, no one knows. What scientists do know is that both animals vanished at roughly similar times. Leviathan disappears from the fossil record around 5 million years ago. Megalodon disappears somewhere between 3 and 4 million years ago. The leading explanation ties both extinctions to the same cause, the closure of the Central American Seaway. When North and South America connected and sealed off the gap between the Atlantic and Pacific Oceans, global current patterns shifted, water temperatures dropped, the warm, prey-rich seas that had supported both giants cooled and became less productive. The large whale populations that fed them collapsed. Both predators starved out. Two giants, millions of years of dominance, and then gone within a few million years of each other because the ocean changed beneath them. But before either of them existed, something older ruled those waters. Something that looked less like a shark or a whale and more like a nightmare pulled from a fever dream. When fossil hunters first dug up Basilosaurus bones in Louisiana in the 1830s, they thought they had found a sea serpent. The bones were so long, so strange, so unlike anything alive, that the scientist who named it called it king lizard, assuming it was some ancient reptile. They were wrong about the reptile part, but they were right about the king part. Basilosaurus was a whale, one of the earliest whale species dating back roughly 40 million years, and it was shaped like nothing alive today. Where modern whales are torpedo-shaped and compact, Basilosaurus was long and serpentine. Some individuals stretched to 60 feet in length, but the body was narrow and flexible, more like an enormous eel than a whale. It moved through the water by undulating its spine, the way a snake moves on land, except in a creature the size of a telephone pole. The skull was over 5 feet long. The teeth were different in the front versus the back of the mouth, which is unusual for mammals. Front teeth were cone-shaped for grabbing. Back teeth were serrated and triangular for slicing. Basilosaurus did not swallow prey whole. It bit into large animals and tore pieces off, the way a crocodile death rolls to remove chunks of meat. What it ate is documented in remarkable detail. Scientists found the stomach contents of a Basilosaurus preserved in Egyptian rock, one of the rarest finds in all of paleontology. Inside the stomach were the bones of smaller whale species called Dorudon, young ones. Basilosaurus was hunting juvenile whales, biting through their skulls with its serrated back teeth. The skull bones of the young whales bore puncture marks that matched Basilosaurus teeth exactly. This is one of the only times in prehistoric predator science where we have direct evidence of a specific predator eating a specific prey animal. Preserved in stone for 40 million years, sitting in a museum in Egypt right now. The body plan of Basilosaurus had one major weakness. That long, flexible spine made it a powerful swimmer in a straight line but a slow turner. It probably could not accelerate out of trouble the way a dolphin can. Scientists think it hunted by patience, following prey, wearing them down, or ambushing juvenile whales that had not yet learned to avoid it. Basilosaurus had tiny hind legs, vestigial ones, barely a foot long, with small toes, dangling uselessly behind its enormous body. Those legs could not support its weight on land. They were evolutionary leftovers, proof that its ancestors had walked on solid ground. 40 million years ago, a 60-foot sea predator was swimming through warm ancient seas with tiny, useless legs. By the time Leviathan and Megalodon arrived, Basilosaurus had been gone for millions of years. But the whale lineage it represented kept going, kept growing, kept evolving teeth and size and intelligence. Leviathan was, in a real sense, the descendant of what Basilosaurus had started. And even stranger creatures had ruled the oceans before Basilosaurus ever existed. 66 million years ago, while dinosaurs still walked on land, a different kind of monster ruled the sea. It was a lizard, an actual lizard, related to modern monitor lizards and Komodo dragons, but stretched to the size of a city bus and built for open ocean hunting. Scientists call it Mosasaurus, named after the Meuse River in the Netherlands where the first skull was found in the 1700s. That original skull sat in a nobleman's private collection for years before scientists realized what it was. When they finally examined it properly, they found something alarming. The teeth were thick, conical and ridged, designed to crush rather than slice, and there were 2 rows of teeth on the roof of the mouth, called palatal teeth, pointing backward like hooks. Anything that went into that mouth was not coming back out. Mosasaurus grew to around 55 feet in some estimates, though the honest scientific range puts most adults between 35 and 50 feet. The body was sleek and paddle-shaped, with 4 large flippers and a tail fin shaped like a crescent. Scientists once thought it swam by undulating its tail like a modern croc, but newer research suggests it moved more like a shark, using powerful side-to-side sweeps of its tail to generate bursts of speed. The bite force measurements on Mosasaurus are extraordinary. Using skull dimensions and muscle attachment points, scientists estimated a bite force exceeding 13 tons of pressure per square inch for the largest individuals. For comparison, a modern crocodile generates around 3,700 pounds per square inch, already enough to snap a human femur instantly. Mosasaurus bit down with 3 times that force. It could crush a car door. What it hunted was everything. Fossil sites from the late Cretaceous period contain Mosasaurus bite marks on sea turtles, large fish, plesiosaurs, ammonites with shells over 3 feet across, and other Mosasaurus. It was an opportunistic apex predator with the jaw strength to handle almost any prey item in its environment. Some bite marks on large turtles show spiral fractures in the shell, the kind of damage you get from a crushing bite that the animal then twisted with its full body. The teeth replace themselves continuously, the same way shark teeth do. A Mosasaurus never ran out of teeth. Every few months a new set pushed the old ones out. Over a lifetime it cycled through hundreds of teeth, which is why Mosasaurus teeth are among the most common large fossil finds in certain rock formations. Mosasaurus disappeared in the mass extinction 66 million years ago, along with the non-bird dinosaurs. When that asteroid hit and the dust blocked sunlight for years, the ocean food chain collapsed from the bottom up. Mosasaurus needed enormous amounts of prey to survive. When the prey vanished, Mosasaurus followed within a geological instant. For over 20 million years before that extinction, Mosasaurus had been the unchallenged king of the open ocean. Almost nothing could challenge it directly, except one thing. A creature that had been building its bite force for millions of years and eventually produced something that still holds a record today. In 2006, fossil hunters working the frozen cliffs of Svalbard, a Norwegian island deep inside the Arctic Circle, found something buried in rock that had been underwater 150 million years ago. A flipper, then another flipper, then a skull nearly 10 feet long with teeth the size of cucumbers. They nicknamed what they were finding Predator X. The official scientific name is Plesiosaurus funki, but the nickname stuck because it captured what the animal actually was. Scientists spent years carefully removing rock from the bones, and what emerged changed estimates for maximum pliosaur size permanently. Pliosaurs were a group of ancient sea reptiles, distant cousins of the plesiosaurs, with a body plan built for pure aggression. Short neck, enormous head, 4 powerful flippers that generated thrust the way a penguin flies underwater, pulling through the sea with controlled power rather than thrashing. The head and neck of a pliosaur could make up a quarter of the entire animal's length. That front-loaded design meant the jaw could generate force from the full weight and muscle of the upper body. Predator X reached an estimated 40 to 50 feet in length. A significant portion of that length was skull and jaw. Scientists used a computer model to simulate the jaw mechanics and calculated that the bite force exceeded 47,000 pounds per square inch. For comparison, the strongest bite force ever recorded in a living animal belongs to the saltwater crocodile at around 3,700 pounds per square inch. Predator X bit down with roughly 12 times that force. The number is so large it is almost impossible to picture. Picture it this way. The armour on a modern military tank is designed to stop rounds travelling at high speed. Predator X's bite force, applied to a single point, would punch through that armour. The teeth themselves were each around a foot long, thick and slightly curved. Serration on the edges, built for penetrating and holding, not slicing. Scientists found healed bite marks on the bones of other large marine reptiles from the same era, the kind of wounds an animal survives and lives with. Those healed marks suggest Predator X attacked prey that was already very large, things that could survive a single bite and keep fighting. The hunts were probably brutal and extended. The body of Predator X was barrel-shaped, built for power over speed. It was likely an ambush predator that relied on short, explosive bursts rather than long chases. Those 4 flippers, driven by massive chest muscles, could generate enormous acceleration from a standing position. Prey never saw it coming from below. Svalbard, where the fossils were found, was tropical ocean 150 million years ago. Rich, warm, teeming with ichthyosaurs, plesiosaurs, and large fish. Predator X sat at the top of that entire ecosystem. Anything in that sea was potential prey, and yet Predator X was large even for its own group. Other pliosaurs existed that were smaller, but arguably more frightening because of where they hunted. The top of the ocean gets light. Sunlight penetrates the first 200 feet of clear water well enough for animals to see each other clearly. But past 200 feet, light fades fast. By 300 feet down, the water is a dim blue twilight where shapes are shadows. By 600 feet, it is complete darkness. Predator X lived in a sea that averaged around 300 to 400 feet deep across much of its range. That means a significant portion of its hunting happened in near darkness, 50 feet below where sunlight could help it, 50 feet above where echolocation would have been an advantage. In that dim middle zone, Predator X relied on senses that scientists are still working to understand. Pliosaur skulls have a feature called sensory pits along the snout, similar to what modern crocodilians have. In living crocodiles, those pits detect tiny pressure changes in water, vibrations too small for most animals to notice. A fish swimming 20 feet away creates ripples in the water column. A whale breathing at the surface creates pressure waves that travel down. A pliosaur with functioning sensory pits could detect prey it could not see, tracking the pressure wake of a moving animal through dark water. Scientists found evidence in Predator X's inner ear structure, suggesting it was tuned for low-frequency sounds, the kind that travel well through deep water and carry over long distances. That inner ear design is also found in modern sperm whales, which hunt giant squid in complete darkness using sound. Two completely different animals, separated by 150 million years, arriving at the same sensory solution to the same problem. The hunting strategy scientists pieced together from those clues goes like this. Predator X waited in deep water, possibly near a shelf or drop-off where prey animals would swim above it. It detected the vibrations of a swimming ichthyosaur or large fish through its sensory pits. It began rising slowly, tracking the pressure wake. At around 100 feet below its target, it stopped rising and matched speed, following silently. Then it accelerated, driving upward, closing the final distance in a burst that lasted less than 3 seconds, and hit prey from below with the full force of those 47,000 pounds per square inch. The ambush from below is confirmed by bite marks. Multiple fossil ichthyosaurs from the same region show impact wounds on the underside of their bodies, wounds inflicted by upward-moving jaws. The attacks came from below. Predator X was a deep water ambush predator that hunted by sound and pressure in near darkness. What makes this especially unsettling is the success rate. Modern ambush predators that attack from below, like great white sharks, have a very high first strike success rate because prey rarely detects them until contact. Predator X had the same advantage. Its first bite was almost certainly its only bite. One hit with those jaws on any soft tissue and the prey was finished. For over 30 million years that strategy worked perfectly. But even with that enormous skull and that crushing bite, Predator X was operating in a world where other pliosaurs had carved out their own deadly domains. If Predator X was the deep ocean killer, Kronosaurus was the shallow water executioner. Roughly 112 million years ago, in the warm, shallow seas that covered what is now inland Australia, Kronosaurus hunted in water you could almost stand in if you were brave enough to try. Kronosaurus queenslandicus was named for the Australian state where its fossils were first found. It reached around 30 feet in length, significantly smaller than Predator X, but with proportions that made it a different kind of terrifying. The skull made up nearly a third of the total body length, 30 feet of pliosaur, 10 feet of which was pure jaw. The teeth were thick cylinders, rounded rather than flat, designed more for crushing and puncturing than for slicing. Scientists used those tooth shapes to work out what Kronosaurus ate. Smooth, rounded teeth work well on hard prey. Turtles, ammonites, fish with heavy bone armor. Kronosaurus was a generalist in the best possible way. It could eat almost anything in its environment, and everything in its environment was trying to avoid it. The shallow sea advantage was about speed and surprise. Kronosaurus could accelerate from stillness to full speed in less than a body length, about the same explosive burst as Predator X, but in water shallow enough that prey had nowhere to dive. When you're in 30 feet of water and a 10-foot jaw surges at you from below, diving deep is not an option. The only escape is sideways or to the surface. Kronosaurus probably herded prey toward the surface intentionally, cutting off the escape route. Fossils of Kronosaurus show something remarkable. Gut contents preserved in rock included the vertebrae of another smaller plesiosaur. Kronosaurus ate other sea reptiles. It swallowed them in pieces, biting through the spine to disconnect sections and then gulping those sections whole. Scientists in the 1930s found a partial Kronosaurus skull in Queensland and were so excited they used dynamite to remove it from the rock. The result was a spectacular but slightly damaged specimen that sat in a Harvard museum for decades, misassembled with extra vertebrae added to make the animal look longer than it actually was. The corrected length is still impressive. The Harvard version was just showboating. The ecological role Kronosaurus played matters beyond its individual hunts. As an apex predator in shallow water, it controlled the population size of every species below it in the food chain. When an apex predator disappears, The animals it was eating multiply unchecked. When Kronosaurus went extinct with the other pliosaurs near the end of the Cretaceous period, the shallow seafood chains it had held in balance reorganized entirely. The question of what replaced it is interesting because nothing directly comparable ever evolved again. Today's shallow coastal waters have large sharks and orcas, but nothing with a skull that is 1/3 of its body length, hunting with the kind of bone-crushing force Kronosaurus carried. But pliosaurs and mosasaurs were relative newcomers in geological time. Before them, other ancient fish ruled waters so different they barely resembled the modern ocean. Not every prehistoric predator was a killing machine. Some animals grew to enormous sizes and chose a completely different strategy. Shastasaurus was the largest marine reptile ever discovered, stretching to around 70 feet in length, longer than a blue whale, longer than any other ocean creature scientists have confirmed in the fossil record. And it probably ate tiny squid. Shastasaurus was an ichthyosaur, a group of reptiles that evolved from land animals roughly 250 million years ago and returned to the sea so completely that their bodies converged on the same torpedo shape as dolphins and sharks. They gave birth to live young in the water. They breathed air but likely dove deep. Their eyes were the largest of any vertebrate animal ever, some individuals with eye sockets over 10 inches across, designed for seeing in near darkness. The biggest Shastasaurus specimens, found in Nevada and British Columbia, come from rock 210 million years old. The animal had a small, toothless or nearly toothless skull relative to its body size, with a narrow snout designed for suction feeding. Picture a sperm whale-sized animal using its mouth like a vacuum cleaner, sucking in soft prey items like squid and fish without biting. That feeding strategy allowed Shastasaurus to grow enormous without competing with the other predators of its era. If you eat tiny things, you do not compete with animals that eat large things. You can share the same ocean without conflict because you are eating from a completely different layer of the food web. The size itself may have been protective. At 70 feet and tens of thousands of pounds, very few predators would risk attacking a full-grown Shastasaurus directly. Even the large predatory sea reptiles of the Triassic period would have had trouble making contact with something that large. Growing huge becomes its own defense when it costs more energy to attack you than any predator would gain from the meal. Scientists found a group of Shastasaurus specimens clustered together in a Nevada rock formation, multiple individuals of different sizes preserved in the same deposit. Whether that means they lived in social groups the way modern sperm whales do, or simply died together in the same event is debated, but the cluster hints at behaviour more complex than simple solitary existence. Here is the truly strange part. Shastasaurus went extinct around 200 million years ago, well before most of the predators in this list even existed. It lived in the Triassic Ocean, before dinosaurs dominated the land, before flowering plants existed, before birds evolved. The world it lived in was so different from today that almost nothing you know about Earth applied, and yet it grew to the largest confirmed size of any marine animal in the fossil record, bigger than any creature alive today, in an ocean 200 million years old. The ichthyosaur group survived for another 150 million years after Shastasaurus, shrinking and diversifying, producing dolphins of the Mesozoic. But they eventually vanished, leaving the seas they had dominated to new rulers. In 1999, a BBC documentary aired a scene that entered internet legend. A pliosaur called Megalodon was depicted as 80 feet long, larger than any animal ever known, dwarfing every other creature in its Jurassic Sea. Millions of people watched it. The number spread everywhere. Megalodon became, in popular culture, the largest predator that ever lived. The actual fossil evidence puts the largest known Megalodon at around 20 to 25 feet. A few teeth and partial skulls suggest some individuals might have reached 33 feet. 25 to 33 feet is still an enormous, genuinely terrifying predator. It would fill a school hallway. Its skull alone would reach from one end of a classroom to the other, but 80 feet. The fossils do not support it. The BBC estimate came from extrapolating a single large tooth found in France in the early 1900s. Scientists tried to scale the tooth up to a complete animal and arrived at a wildly inflated number. Later fossil finds gave researchers actual skull and body material to work with, and the recalculated size dropped dramatically. This matters beyond just correcting a mistake. It is a window into how science works. Early estimates based on limited evidence often overreach. When more evidence arrives, estimates get revised. That revision is the system working correctly. The documentary makers took the largest possible number from incomplete data and presented it as confirmed fact. Real science presented a range and updated it when new information arrived. Leopleurodon, at its actual confirmed size, was still a remarkable predator. It lived around 160 million years ago in the warm, shallow sea that covered what is now Central Europe. Scientists found its fossils in England, France, and Germany, in rocks that were once seafloor. It had 4 large flippers, a relatively short neck for a pliosaur, and conical teeth up to 3 inches long. It could open its jaws wide enough to swallow prey nearly half its own body length. The vision of Leopleurodon was probably exceptional. A brain endocast, which is a fossil cast of the inside of a skull showing brain shape, reveals large olfactory bulbs at the front of the brain. Those bulbs process smell. Leopleurodon likely tracked prey by scent the way modern sharks do, picking up chemical traces in the water and following them to the source. The corrected size of Leopleurodon reminds us that the real animals are already remarkable without exaggeration. An animal the size of 2 cars with 3-inch teeth, hunting by smell in a warm Jurassic Sea, was a genuine terror. The ocean does not need inflated numbers to be terrifying. What the ocean does have is animals whose real sizes are almost harder to believe than the inflated ones. Animals with weapons so strange that no one who found the first fossil understood what they were looking at. 375 million years ago, the oceans were full of fish in armour. The Devonian period was the age of armoured fish, called placoderms, and they dominated every sea on the planet. The largest, the most powerful, and by far the most frightening of all of them was Dunkleosteus torelli. Dunkleosteus was not a shark. It was an armoured fish, and the difference matters. Where sharks have cartilage skeletons, Dunkleosteus had a head encased in thick, bony plates, fused together into a rigid shield that protected its skull and the front of its body. Behind that armour, the rest of the body was soft and flexible. The armour plates have been found fossilised all over the world. The soft body rarely preserved, so most of what scientists have is the front half of the animal. From the armour alone, scientists estimate Dunkleosteus reached around 20 feet in length. Not the largest predator in this list, but what it did with 20 feet has no comparison in history. Dunkleosteus had no teeth. 0. Instead, the jaw edges were made of bone sharpened to a razor edge by constant self-sharpening contact. Every time the jaw opened and closed, the upper and lower bony edges honed themselves against each other the way a knife sharpens against a whetstone. The result was a perpetually sharp, self-maintaining blade that grew continuously throughout the animal's life. The jaw mechanics were studied by scientists who built a mechanical model of the skull and measured the speed and force. The results were stunning. Dunkleosteus could open its jaws in 50 milliseconds. That is roughly 20 times faster than a human blink, and it did not open just its lower jaw. The entire front skull plate rotated upward, while the lower jaw dropped simultaneously, creating a gaping opening in less than 1/10 of a second. The suction created by that opening literally pulled prey into the mouth before the animal even made contact. The bite force at the jaw tips reached around 8,000 pounds per square inch for the largest individuals. That was enough to cut through the thick bone armour of other placoderms, which were the primary prey. Scientists found armoured fish bones in Devonian rock with clean slicing cuts that matched Dunkleosteus jaw edges exactly. It ate other armoured fish by slicing through their armour. Fossil sites in Cleveland, Ohio contain hundreds of partial Dunkleosteus specimens preserved together. Scientists found stomach contents near some of them, regurgitated masses of half-digested armoured fish. Dunkleosteus swallowed chunks it could not fully digest, then vomited up the bony material the same way owls regurgitate pellets of mouse bones. Cleveland was at the bottom of a warm inland sea 375 million years ago, and Dunkleosteus ruled it completely. When the Devonian period ended in a mass extinction event, Dunkleosteus vanished. But the armoured fish era it represented was replaced by something even more alien. The Devonian period lasted from about 419 million years ago to 359 million years ago, 60 million years of ocean, and almost every major evolutionary innovation in sea predators either appeared or matured during this stretch of time. Jaws evolved during the Devonian. The first jawed fish appeared just before this period and diversified explosively during it. Before jaws, ocean predators used suction, filtering, or weighting. Jaws allowed active pursuit hunting. The moment jaws appeared, the ocean reorganized around them. Animals with jaws ate animals without jaws. The jawless animals were pushed to the margins. Fins evolved into something close to limbs during this period. Some fish developed thick, muscular fins they could prop themselves on in shallow water. By the end of the Devonian, some of those fish were dragging themselves onto land, starting the 400 million year process of vertebrates colonizing the Earth. Every land animal alive today traces its ancestry to a fish from the Devonian period. Every mammal, every reptile, every bird, including you, is the evolutionary descendant of an armoured fish swimming in a Devonian sea. But the ocean itself during this period was stacked with predators at every level. Dunkleosteus dominated large prey. Smaller placoderms filled middle-sized niches. Early sharks, still primitive compared to modern ones, were already present and multiplying. Predatory sea scorpions called eurypterids grew to 8 feet long and hunted in estuaries and coastal shallows. The competition for prey was intense at every size category. The oxygen levels in Devonian ocean water were lower than today in some regions, which stressed the bodies of fish that depended on efficient breathing. Some species adapted by developing primitive lung structures, which eventually led to the evolution of true lungs in land vertebrates. The environmental pressure of the Devonian Sea literally drove fish onto land. The Devonian ended in a mass extinction called the Late Devonian extinction. Around 3/4 of all species on Earth vanished over roughly 20 million years. The causes are still debated. Ocean warming, loss of oxygen in deep water, changes in sea chemistry. Whatever happened, it reset the biological diversity of the planet dramatically. Dunkleosteus and the armoured fish went with it. But sharks survived. Early sharks had been present in the Devonian, and they made it through the extinction. They kept going. They are still here. The sharks alive today carry an unbroken genetic lineage that runs back through the Devonian extinction, through the extinction that killed the dinosaurs, through every major reset the planet has experienced. They survived everything. But in the seas of the Devonian and the period just before it, even the earliest sharks were overshadowed by something so strange that scientists spent over a century arguing about what part of the animal they had even found. In 1899, a geologist working in Idaho found a fossil coiled like a watch spring, about the size of a dinner plate. It was made of teeth, hundreds of teeth, arranged in a perfect spiral, each one serrated, each one slightly larger than the one before it, the whole structure curling inward from the outside edge to a tiny point at the centre. Nobody had any idea what it was. For over 100 years, scientists placed that spiral tooth structure in every possible location on the animal. Some said it was a lower jaw, some said it was on the tip of the nose, some placed it at the front of the snout sticking out like a chainsaw. Artwork of Helicoprion from that era looks like something from a nightmare. An animal with a spinning saw blade hanging off its face. The answer finally came in 2013, when scientists got access to an exceptionally preserved specimen and used a scanning technique that allowed them to see inside the rock without destroying the fossil. The tooth spiral sat at the back of the lower jaw, coiling backward and downward into the throat. The upper jaw had no teeth at all. Helicoprion bit down with a smooth upper jaw, while the spiral in the lower jaw rotated like a circular saw blade as the mouth closed, slicing through soft prey. The prey was most likely soft-bodied cephalopods, ancient relatives of squid and ammonites. Helicoprion lived around 270 million years ago, before Dunkleosteus' era ended, in the oceans of what is now Idaho, Russia and Australia. The ocean covered Idaho then. The Rockies did not exist yet. The spiral structure itself is a biological rarity. Sharks continuously shed their teeth. Old teeth fall forward, and new ones replace them from behind, the same conveyor belt system that replaces Megalodon teeth. Helicoprion did not shed its teeth. As new teeth grew at the base of the spiral, they pushed the old ones forward and outward, building the coil. An old Helicoprion might have a spiral of hundreds of teeth, the outermost ones the oldest and smallest, the innermost ones brand new. The whole structure stayed in the mouth for life. The largest Helicoprion spirals found have a diameter of around 18 inches. Scientists use the spiral size to estimate body length. A spiral that size suggests a shark around 25 feet long. The body plan was probably similar to a modern shark from the torso back, but the head and jaw arrangement was unique to this animal and has never reappeared in any other species before or since. Helicoprion survived one of the greatest extinction events in Earth's history, the Permian extinction, which killed over 90% of all marine species. After that extinction, it lived for another 10 million years before eventually disappearing. An animal with a built-in saw blade in its throat, surviving the worst mass extinction the planet ever produced. But even Helicoprion pales next to the creatures that came long before it, in a sea so ancient that the world barely looked like Earth at all. 520 million years ago, there were no fish, no sharks, no whales, no sea reptiles. Nothing with a backbone existed in the ocean at all. Vertebrates had not been invented yet. The sea was full of soft-bodied animals, worms and jellyfish and strange creatures that left no modern relatives, animals so alien that when scientists found their fossils in the Canadian Rockies in the late 1800s, they initially described the different body parts as separate species. They found a circular mouth ring and called it a jellyfish. They found a pair of grasping appendages and called them shrimp. They found a segmented body and called it a worm. It took decades before anyone realized all three pieces belonged to the same animal. That animal is Anomalocaris, which means abnormal shrimp, a name that stuck from the early misidentification of the arm fossil. Anomalocaris was the largest known predator in the Cambrian Sea, the ocean of 520 million years ago. It grew to around 3 feet in most species, with some reaching 6 feet. That does not sound enormous until you understand that everything around it was measured in inches. Against the background of Cambrian life, a 6-foot Anomalocaris was the equivalent of a blue whale cruising through a pond of goldfish. The body plan had no equivalent today. 2 large stalked eyes, each on a separate arm extending from the head. A circular mouth ringed by plates that closed together like a camera aperture, surrounded by a ring of teeth. 2 large grasping appendages at the front, covered in spines for catching and gripping prey. A flat, segmented body with rows of overlapping gill plates along the sides. It swam by undulating those gill plates, moving through the water like a living, segmented magic carpet. The eyes of Anomalocaris were extraordinary. Scientists found fossilized eyes preserved in rock, and each eye contained over 16,000 individual lenses. Modern dragonflies have around 28,000, giving them nearly 360-degree vision. Anomalocaris may have had similar visual coverage, seeing almost everything around it simultaneously. For a predator in an open water environment with no places to hide, that visual system was a massive advantage. What it ate includes trilobites. Trilobites were small, hard-shelled creatures abundant in Cambrian seas, and fossil trilobites from this period show bite marks that match Anomalocaris' circular mouth pattern exactly. The grasping arms caught the trilobite, the mouthplates closed around it, and those teeth cracked the shell. Researchers debated for years whether the mouth was strong enough to crack shells. Computer modelling eventually confirmed it was, though only on smaller trilobites. Anomalocaris eventually evolved into more specialised forms, and its lineage gave rise to modern arthropods, the group that includes crabs, lobsters, insects and spiders. The grasping arms it used for hunting are the evolutionary ancestors of the claws on every crab in every ocean right now. But even Anomalocaris needed to come from somewhere, and where it came from is one of the most dramatic events in the history of life on Earth. For the first 3.5 billion years of Earth's history, the oceans held nothing that would scare you. Bacteria, simple algae, single-celled organisms drifting in warm, shallow seas. For most of Earth's existence, the most complex life on the planet was a mat of bacteria clinging to a rock on the seafloor. Then, around 540 million years ago, something happened that scientists still argue about. In the span of about 20 million years, an eye blink in geological time, almost every major body plan in the animal kingdom appeared simultaneously in the fossil record. Eyes, legs, shells, claws, jaws, gills, fins, nervous systems. Everything that would eventually evolve into every animal on Earth showed up in the same narrow window of time. This event is called the Cambrian explosion, and the central mystery is why it happened so suddenly after so long. One leading answer is predation itself. The first predators created the first evolutionary pressure for defense. Once one species developed a mouth that could eat another animal, every other species faced a survival choice: develop armor, develop speed, develop senses to detect the threat, or get eaten out of existence. The moment predation appeared, evolution accelerated. Every defensive adaptation created pressure for a better offensive adaptation. Every offensive improvement created pressure for stronger defense. The arms race started and has never stopped. Before the Cambrian, there were almost no predators because there was almost nothing complex enough to prey on. The step from bacterial mat to complex animal took billions of years because there was no external pressure forcing rapid change. Life was slow, chemical, microscopic. When the first complex multicellular animals appeared, the predator-prey dynamic kicked in and complexity snowballed. The Cambrian ocean that resulted from this explosion was brutally competitive. Anomalocaris was the apex, but below it was a hierarchy of shells and spines and eyes and armor, every creature in a constant arms race with everything around it. Animals evolved eyes so they could see predators. Predators evolved better eyes so they could spot prey that was hiding. Prey grew shells. Predators grew stronger mouths to crack shells. Every adaptation drove the next counter-adaptation. The fossil record from this period is preserved in extraordinary detail in a few locations around the world. The Burgess Shale in Canada and similar sites in China contain soft-bodied creatures from the Cambrian, preserved in such perfect detail that scientists can see the outline of internal organs in some specimens. Those fossils read like a catalogue of alien life, forms that existed for millions of years and then vanished completely, body plans that evolution tried and abandoned. The Cambrian explosion is the moment Earth's oceans became predatory ecosystems. Every predator in this list, from Anomalocaris forward, is a descendant of the evolutionary pressure that started 540 million years ago when the first complex animal ate the second one. The predators that came after the Cambrian kept getting bigger, smarter, and more specialized. And some of the most extreme examples appeared much later, when the ocean spilled onto the land and a new kind of giant claimed both worlds at once. For most of the 20th century, scientists thought they understood Spinosaurus. A large meat-eating dinosaur walked on two legs, probably hunted like a bigger version of a crocodile near riverbanks. Interesting, but straightforward. Then a series of fossil discoveries starting in 2014 turned that picture completely upside down. Spinosaurus aegypticus was first discovered in Egypt in 1912, by a German paleontologist who shipped the bones to Munich, where they were destroyed in a World War II bombing raid. For decades, scientists worked from old drawings and partial fragments. Then, new material surfaced in Morocco, and everything changed. The updated Spinosaurus reached around 50 feet in length, making it the largest carnivorous dinosaur ever found, longer than Tyrannosaurus rex by around 10 feet. But the body was radically different from any other large meat-eating dinosaur. The legs were short and dense, built for swimming, not running. The feet had wide, flat toes that may have been partially webbed. The centre of gravity sat low and forward. On land, Spinosaurus would have moved awkwardly, leaning forward like an enormous crocodile trying to walk. In water, it made complete sense. The skull was long and narrow, nearly 6 feet, shaped almost exactly like a modern gharial, the thin-snouted crocodilian that specialises in catching fish. Conical teeth with no serration, perfect for gripping slippery fish but useless for slicing through large prey. Nostrils positioned high on the skull so the animal could breathe while most of its head was submerged. The spine is where Spinosaurus gets its name. Neural spines extending up from the vertebrae reached over 5 feet tall, forming a massive sail or hump along the back. Scientists debate the function. Some say heat regulation, some say display for attracting mates, some suggest a fat-filled hump like a camel's. Whatever the purpose, those spines were visible from a distance, making Spinosaurus one of the most visually distinctive animals ever to exist. Fossil sites in Morocco show that Spinosaurus lived near a massive river system 100 million years ago, a river larger than the modern Amazon, running through what is now the Sahara Desert. That river teemed with enormous fish, including one species called Oncha pristis, a sawfish with a snout lined with serrated spines that reached over 20 feet long. Spinosaurus hunted these fish the way a grizzly bear fishes for salmon, wading into the current, snapping up prey from the water. But here is what makes Spinosaurus genuinely unlike any other dinosaur. The bone density in its legs was extremely high, denser than any other large dinosaur measured. Dense bones reduce buoyancy. Spinosaurus sank into water rather than floating, the same adaptation found in modern hippos and some diving birds. Scientists believe Spinosaurus spent the majority of its life in water, not beside it. A creature the size of 2 large African elephants, built to swim in a river the size of the Amazon, hunting fish the length of a school bus. And this was a dinosaur, an animal that had evolved from small landrunners and reversed its entire body plan back toward the water over millions of generations. Spinosaurus shared its river with something else, something much older in design, already perfected for water long before dinosaurs existed, and growing to sizes that strain belief. The first massive Sarcosuchus skull turned up in the Sahara Desert in the 1960s during a French expedition. The skull alone measured 6 feet long. The scientist who found it knew immediately they were looking at a crocodilian, but the proportions were wrong for anything alive. This was not a big crocodile. This was something else. Sarcosuchus imperator lived around 112 million years ago, in the same river systems that Spinosaurus patrolled. Full-grown individuals reached around 40 feet in length and weighed roughly 18,000 pounds, about the same as 3 adult African elephants side by side. A modern Nile crocodile, already the largest living reptile on Earth, reaches around 16 feet and 2,000 pounds. Sarcosuchus was more than twice as long and 9 times heavier. The skull was lined with over 100 teeth, each one interlocking with a corresponding tooth from the opposite jaw, creating a trap that could not release once closed. The rear of the skull had a bulbous bump called a bulla, whose function is still debated. Some scientists think it may have housed sensory cells, giving Sarcosuchus an enhanced ability to detect vibrations from animals approaching the water's edge. If that interpretation is correct, Sarcosuchus could sense a dinosaur walking nearby before it ever saw or smelled it. The eyes sat on top of the skull, angled upward and slightly outward, exactly like a modern crocodile. This confirms the ambush strategy. Sarcosuchus sat submerged with only its eyes and nostrils above water, watching the bank. When a large animal came to drink, it exploded from the water in a lunge, grabbed the prey in those interlocking jaws and dragged it back in. The death roll followed. Sarcosuchus twisted its entire body while holding its prey, using rotational force to remove chunks of flesh or drown the animal completely. The prey that came to drink at those Cretaceous rivers included mid-sized dinosaurs. Bone fragments from dinosaurs of that era found near Sarcosuchus. Fossil sites show characteristic crocodilian bite marks, circular punctures, then drag marks where the bone was pulled against the teeth. Scientists found evidence that Sarcosuchus targeted dinosaurs up to its own size. Sarcosuchus reached full size slowly. Scientists can read growth rings in bones the same way you read rings in a tree trunk, each ring representing 1 year of growth. The largest Sarcosuchus specimens show around 50 or 60 growth rings, meaning the animal took 50 years to reach full adult size and then kept growing. A 60-year-old Sarcosuchus was still getting bigger. That slow growth meant young Sarcosuchus were vulnerable for decades. Juveniles had to stay in shallow water where large predators could not follow, growing incrementally, surviving on fish and small animals until they were large enough that nothing would bother them. What lived alongside Sarcosuchus was its African counterpart, an animal from a different continent that somehow managed to grow even larger, with a bite force so extreme that scientists measured it and then checked their calculations twice before publishing. 8 million years ago, South America was an island continent. The land bridge connecting it to North America had not formed yet. Cut off from the rest of the world, the animals in South America evolved in isolation for tens of millions of years, producing creatures found nowhere else on Earth. The rivers of that isolated continent, fed by an Amazon basin that was larger and wetter than today, produced the largest crocodilian that ever lived. Purosaurus brasiliensis reached around 41 feet in length, a fraction longer than Sarcosuchus, but far heavier, with a skull nearly 5 feet wide and a body so massively built that scientists estimate it weighed close to 20,000 pounds. To put that number in context, a modern hippopotamus, one of the most dangerous animals in Africa, weighs around 3,300 pounds. Purosaurus outweighed 6 hippos. The bite force was calculated using skull dimensions and muscle mass estimates. The result came out at around 7 tons of force, making Purosaurus's bite the strongest measured for any animal in the fossil record, exceeding even the estimates for Predator X at the jaw tips. At the back of the jaw, where the teeth are closest to the hinge and leverage is maximized, the force per tooth was enough to punch through solid steel beams. But Purosaurus did not hunt animals that required maximum bite force to kill. It hunted by grab and drown. The strategy was the same as modern crocodilians, but scaled to monstrous proportions. Grab the prey anywhere on the body, drag it into water, hold it under. For an animal weighing 20,000 pounds with a jaw locked around your leg, no amount of struggling would help. The outcome was fixed from the moment of contact. The prey available to Purosaurus in Miocene South America included giant ground sloths, early relatives of modern tapirs, giant rodents the size of cows, and ancestral horses that had evolved in South America before going extinct there and being reintroduced from North America millions of years later. A Purosaurus lying still in a river looked like a floating log. Every animal that came to drink was within range. Fossil sites along the Amazon and Orinoco river basins in Brazil and Venezuela have produced multiple Purosaurus specimens, including juveniles, suggesting a stable population sustained by the extraordinary richness of Miocene South American rivers. The rainforest was even larger then, feeding rivers that may have been wider and deeper than any river on Earth today. Purosaurus eventually went extinct as South America's climate dried slightly, and the enormous river systems it depended on shrank. When the land bridge to North America formed around 3 million years ago, North American predators poured south and competed with the animals that had evolved in isolation. The ecological balance that had supported a 20,000-pound crocodile shifted. But while Purosaurus and Sarcosuchus were the giant crocodilians of their respective times, and Spinosaurus was reinventing what a dinosaur could be, the entire age of dinosaurs was approaching its end, and the extinction that killed them revealed something about which ocean predators were truly built to last. 66 million years ago, an asteroid around 6 miles wide hit what is now the Yucatan Peninsula in Mexico at around 45,000 miles per hour. The impact released energy equivalent to billions of nuclear weapons simultaneously. Rock vaporized and shot into the upper atmosphere, circling the globe. Wildfires ignited across entire continents. Dust blocked sunlight for months, then years. Temperatures dropped. Plants died first, then the animals that ate plants, then the animals that ate those animals. Around 75% of all species on Earth went extinct. The non-bird dinosaurs vanished completely, pterosaurs gone. All the large marine reptiles, Mosasaurus, plesiosaurs, pliosaurs, gone within geological moments. Animals that had dominated their ecosystems for hundreds of millions of years disappeared together in a single event. The ocean suffered deeply. Photosynthesis shut down when sunlight disappeared, collapsing the base of the marine food chain. Tiny organisms called phytoplankton, which form the foundation of almost all ocean food webs, died in enormous numbers. Without phytoplankton, the small animals that ate them died. Without those small animals, larger animals starved. The collapse moved upward through the food chain level by level. Mosasaurus needed enormous amounts of large prey. When large prey collapsed, Mosasaurus starved quickly. Its size, which had been an advantage for millions of years, became a death sentence. Large body means high energy requirement. High energy requirement means no tolerance for food scarcity. Sharks survived. They had survived multiple previous extinction events, and they survived this one too. The reason is flexibility. Sharks can eat almost anything and can go months between meals when necessary. Small sharks survived by switching to whatever food remained, scavenging carcasses, eating invertebrates, targeting whatever showed up. Their cartilage skeleton requires less energy to maintain than bone. Their metabolism can slow dramatically. They waited out the collapse. Some marine mammals, the ancestors of modern whales and dolphins, were land animals at the time of the extinction and survived on land. They returned to the sea afterward, eventually producing the giants that came later. Crocodilians survived in rivers and coastal swamps, where decomposing plant material kept some food available at the bottom of the food chain. Sea turtles survived at small sizes. The survivors of the extinction inherited an ocean that was almost empty of large predators. For millions of years after the asteroid, the seas held nothing comparable to Mosasaurus or the pliosaurs. The ocean predator throne sat vacant. Then the mammals arrived. First small, then larger, then enormous. And the ocean filled again, faster than scientists expected, with a new generation of giants. The 10 million years following the mass extinction are sometimes called the early Paleogene recovery period. The ocean during this time was ecologically simple by comparison to what came before and what came after. Large predators were gone. The prey animals that had fed them were gone. The seas held smaller fish, small sharks, early mollusks rebuilding their populations, and the earliest marine mammals just beginning their transition from land to water. The absence of large predators created an ecological vacuum. When no large animal hunts medium-sized animals multiply. When medium-sized animals multiply, the food supply for the next generation of large predators accumulates. The ocean was loading itself for the next round of giants. Scientists track this recovery through the fossil record by measuring the average body size of ocean animals at different points in time. In the first 5 million years after the extinction, average body size dropped sharply. Small animals dominated. Then, around 55 million years ago, average size began climbing again. New lineages were growing larger. The earliest large marine mammals appeared during this window. Pachycetus, the dog-sized wading ancestor of all modern whales, appeared around 50 million years ago. Its descendants got bigger with each generation because bigger meant safer and better fed. The ocean was rich with recovering fish populations, and almost nothing was hunting large prey. The pathway to enormous size had no obstacles. Sharks were already there, maintaining their populations through the lean years on smaller prey, and expanding again as fish populations recovered. The earliest relatives of modern great white sharks appear in the fossil record around 43 million years ago. By 30 million years ago, the ancestors of Megalodon were already reaching significant sizes. The calm period did not last. As prey animals grew larger, predators grew to match them. As predators grew larger, prey evolved faster movement, better hearing, group behaviour. The arms race resumed exactly as it had ended, with the same pressure pushing size in both directions. The transition from post-extinction calm to fully armed Miocene ocean took about 20 million years. By the time Leviathan and Megalodon appeared, the ocean was as competitive and dangerous as it had ever been. The recovery was complete, and a new set of record-breaking giants had taken the places left vacant by the mass extinction. That filling of ecological vacancies is one of the most consistent patterns in Earth's history. Whenever a mass extinction clears the top of the food chain, evolution fills it back in. Different body plans, different strategies, but the same outcome: a large, powerful apex predator ruling the ocean within a few million years. What filled the megalodon-sized vacancy after it went extinct is a different question, with an answer that surprises people. Megalodon did not appear fully formed. It descended from a lineage of increasingly large sharks that can be traced through the fossil record tooth by tooth, layer by layer in the rock, across millions of years of gradual growth. The most important step in that lineage is a shark called Carcharodonts angustidens, Megalodon's direct ancestor, which shows exactly how the largest predatory fish in history got so big. Carcharodonts angustidens lived around 33 to 22 million years ago, during the Oligocene epoch. Adults reached around 30 feet in length, about half the size of the largest Megalodon. The teeth were large, triangular, and serrated, clearly in the same evolutionary line, but narrower and slightly different in proportion. If you lined up the teeth of angustidens and Megalodon side by side, you could see the family resemblance immediately. The teeth of angustidens also have side cusps, small additional points flanking the main blade, a feature that disappeared in Megalodon. Scientists use the presence and absence of those side cusps to track the transition between species across millions of years of fossil layers. As you move forward in time through the rock record, the cusps shrink and eventually vanish. The teeth get wider and taller, and Megalodon gradually emerges. What drove the size increase from angustidens to Megalodon was prey. The Oligocene and Miocene oceans were seeing the rise of larger and larger whale species. Small-toothed whales appeared first, then bigger ones, then the enormous filter feeders. Every time whale body size jumped upward, there was an advantage for any shark large enough to hunt the new size class. Larger sharks got more food, produced more offspring, and passed their size genes forward. Over 10 million years, that pressure accumulated into Megalodon. This process, where predator size tracks prey size over geological time, is called evolutionary escalation. Scientists can watch it happen in the rock record like a slow-motion film. The sharks grow when the whales grow. The whales grow because the ocean is getting more productive. The productivity increases because continental positions are shifting ocean currents and concentrating nutrients. Everything is connected. The size of Megalodon is traceable back to the position of the continents tens of millions of years before Megalodon existed. Angustidens itself was a serious predator. Whale bones from its era show bite marks matching its tooth dimensions. It was already hunting large marine mammals and winning. But the transition to full Megalodon scale made it a different order of animal entirely. The moment Megalodon reached its peak size is identifiable in the rock record. Certain fossil layers contain teeth of a size and proportion that scientists classify as peak Megalodon, the largest individuals hunting the largest prey at the height of the species' power. That peak did not last forever. Around 15 to 10 million years ago, Megalodon reached the height of its power. The Miocene Ocean was warm. Whale populations were large and diverse. The seas from the tropics to the mid-latitudes were full of prey. Megalodon teeth from this period are found on every continent except Antarctica, from the eastern United States to Japan, from Peru to Australia, from the English Channel to the coast of South Africa. The animal was global. At peak Megalodon, individual sharks reached 60 feet in length and likely 100,000 pounds. The teeth from this period measure up to 7 inches, the largest ever found. Those teeth required whales as prey. A shark that size could not meet its energy needs on smaller animals. Scientists calculate that a 60-foot megalodon needed to consume roughly 2,000 pounds of food every day to sustain basic body functions. The hunting strategy at this size was different from smaller sharks. Speed was less important than force. Scientists analysed the jaw mechanics and concluded that Megalodon likely targeted the hard structural parts of large whales deliberately, striking at the pectoral fins to disable the animal's ability to swim, or targeting the skull and ribcage to access vital organs quickly. This is different from how great white sharks hunt today. Great whites go for soft tissue. Megalodon went for the bones. Evidence from whale fossils supports this. Bones of ancient whales from Megalodon's peak era show crushing impacts, not slicing cuts. Impacts powerful enough to shatter ribs 4 inches thick. Impacts applied with enough precision to suggest the shark knew exactly where to strike for maximum damage. Whatever intelligence a 60-foot shark carries, Megalodon used it efficiently. The global range of Megalodon is documented by fossil finds, but the pattern is not random. Teeth cluster in certain regions, specifically areas close to where warm, shallow coastal waters meet productive upwelling zones. Megalodon preferred specific ocean conditions. It needed warm water for its metabolism and abundant prey for its enormous food requirements. When both conditions were met, the fossils are dense. When one condition was absent, the fossils thin out. This geographic preference turned out to be Megalodon's vulnerability. An animal tied to specific ocean conditions cannot adapt quickly when those conditions shift. A shark that needs warm water and abundant large whales has nowhere to go when the water cools and the whales change their migration patterns. The peak of Megalodon was also the beginning of the conditions that would eventually end it. The same warm, prey-rich ocean that allowed it to grow so large was already starting to change as the planet slowly cooled. But before that cooling reached a critical point, the fossil record captured something extraordinary near Peru, something that forced scientists to revise the entire timeline of Megalodon's existence. For most of the 20th century, scientists believed Megalodon went extinct around 2.5 million years ago. That date came from the youngest Megalodon teeth found in the fossil record at the time. The youngest teeth dated to the early Pliocene, and scientists drew the extinction line there. Then, in 2023, a team working a fossil site on the coast of Peru found Megalodon teeth in rock layers that dated to around 3.6 million years ago. That part was expected. But they also found teeth of modern great white sharks in the same layers. Great whites and Megalodon in the same rock, at the same time, in the same ancient coastal sea. This matters because it challenges a long-held idea about why Megalodon went extinct. One popular explanation suggested that great white sharks outcompeted Megalodon by targeting the same prey more efficiently. But if the two species coexisted for millions of years without great whites driving Megalodon out, that explanation weakens considerably. The Peru site also produced teeth in layers spanning several million years, allowing scientists to track changes in tooth size and shape over time. What they found was that Megalodon teeth from later layers were slightly smaller than teeth from earlier layers. The average individual may have been shrinking slightly before extinction, suggesting the population was under stress from declining food availability rather than direct competition. The youngest confirmed megalodon teeth currently in the scientific record come from deposits around 3.3 to 3.5 million years ago. The 2.5 million year date that appeared in textbooks for decades is now considered too recent. The actual extinction appears to have occurred slightly earlier than previously thought, which affects how scientists model the cause. The revised timeline aligns more closely with a period of dramatic ocean cooling connected to the formation of permanent ice sheets in Antarctica and the Arctic. Around 3.5 million years ago, global ocean temperatures dropped sharply. Cold water pushed into what had been warm coastal seas. Whale migration patterns shifted. Prey that had concentrated in shallow warm water moved to follow temperature gradients that Megalodon could not comfortably follow. The Peru fossils also reveal that Megalodon was still present in equatorial waters later than in higher latitudes. The tropics stayed warm longer, and Megalodon held on there while populations collapsed at higher latitudes first. The extinction was not simultaneous globally. It moved from cooler regions toward the equator over hundreds of thousands of years. Every new fossil find adds detail to a picture that keeps getting more precise and more complicated. Scientists are nowhere near a final answer on Megalodon's extinction, and the next discovery could shift the date again. What survived that same cooling event tells a story of a completely different kind of shark. Megalodon and the great white shark shared the ocean for millions of years. They were different animals, different sizes, different body plans, different prey preferences. The great white is not a miniature megalodon. It is a separate species that evolved independently, descended from a different shark lineage. The great white shark today averages around 15 feet and 2,000 pounds. The largest confirmed individuals reach around 20 feet. Against Megalodon's 60 feet and 100,000 pounds, the great white looks almost small, but the great white is still here. Megalodon is gone. The reason reveals something important about what makes an animal truly resilient. Great white sharks eat a wide range of prey: seals, sea lions, dolphins, large fish, marine birds, whale carcasses, smaller sharks. Their preferred prey varies by region and season. They follow prey migrations. They switch prey types when one becomes scarce. This flexibility means a great white can survive a bad year, a cold period, a shift in whale populations by simply eating something else. Megalodon required large whales to meet its energy needs. A 60-foot shark burning enormous calories every day cannot switch to eating seals. The caloric math does not work. When large whale populations in warm coastal waters declined due to ocean cooling, Megalodon's only option was to follow the whales into cooler waters or starve. Cold water slows a large shark's metabolism in ways that are debilitating at Megalodon's size. Great white sharks tolerate cold water because they are regionally endothermic, meaning they generate some body heat internally and can maintain a core temperature above the surrounding water. This allows them to hunt in waters too cold for most fish. Whether Megalodon had this capability is unknown. Soft tissue does not fossilize. Scientists cannot measure Megalodon's heat-generating physiology directly, but its known geographic distribution, avoiding cold water consistently, suggests it lacked the cold water tolerance that great whites possess. The second factor is reproductive strategy. Sharks that birth fewer, larger, more developed young are more vulnerable to population collapse because recovery from a population drop is slower. If Megalodon gave birth to large pups in shallow nursery areas, and those nursery areas were disrupted by cooling or changing coastlines, juvenile survival would have dropped sharply. A species losing its juveniles faster than adults or reproducing declines toward extinction. Great white sharks are smaller, more flexible in prey, tolerant of a wider temperature range, and distributed globally across diverse habitats. They were never dependent on a single prey type or a single ocean condition. They are still here because resilience matters more than size. Megalodon dominated the ocean with raw power for 20 million years. The great white has been doing it for millions of years by being adaptable. Power and adaptability are different survival tools, and in changing environments, adaptability wins. But the ocean today holds something else, something alive right now that most people never think about when they picture ocean giants. In 2007, a New Zealand fishing vessel working in the Ross Sea near Antarctica hauled up something in its nets that took the entire crew to lift. A squid. A single squid, weighing around 1,000 pounds, measuring around 30 feet from tentacle tip to body end. The crew called the nearest research station. Scientists flew out. They took measurements, photographs, samples, and then froze the animal for study. The colossal squid, Mesonychoteuthis hamiltoni, had been known from fragments for decades. This was the first near-complete adult ever captured. The colossal squid is the largest invertebrate on Earth by mass. Its eyes are the largest of any living animal, reaching 10 inches across, larger than a dinner plate. Those eyes are designed for detecting bioluminescence, the faint light produced by deep-sea creatures in water 1,500 feet down where no sunlight reaches at all. The tentacles of the colossal squid are lined with hooks, not suckers. Sharp, rotating hooks set into rings of cartilage that can spin independently, drilling into anything the squid grabs rather than just gripping it. A sperm whale that swallows a colossal squid whole often bears circular scars from those hooks across its skin and the inside of its throat, left behind in the struggle. Most people have never seen a colossal squid alive in the wild. Exactly 0 scientists have observed one hunting in its natural deep-sea environment. Everything known about colossal squid behaviour comes from stomach contents of sperm whales, the occasional individual caught in nets or found floating dead, and some beak fragments found in sediment cores from Antarctic waters. Scientists estimate that colossal squid are abundant beneath the Southern Ocean. Sperm whales in that region eat enormous quantities of them. The population supporting that level of predation must be large. There could be millions of animals in the abyss below Antarctica that humans have never seen and never will, simply because the depth and cold make it nearly inaccessible. The colossal squid is a reminder that Earth's oceans are still largely unexplored. Less than 20% of the deep-sea floor has been mapped with high resolution. The volume of ocean below 3,000 feet is so immense that something the size of a school bus could live its entire life there without ever being detected. If a 30-foot squid can go virtually undetected in 2007, what else is down there that no one has found yet? This question is not just speculation. It is backed by the consistent reality that new large species are still being discovered regularly in ocean depths. But the largest animals alive today are not hiding. They are visible, documented, and in some cases facing extinction. And one of them connects directly to the ancient predators in this list. The sperm whale alive today is the largest toothed predator on Earth. Males reach around 60 feet in length and around 120,000 pounds. The brain of a sperm whale is the largest ever recorded in any animal, weighing around 18 pounds, roughly 6 times heavier than a human brain. It produces clicks loud enough to stun or kill large squid at close range, a form of biological sonar so powerful it functions as both a navigation system and a weapon. Leviathan melvillei, the prehistoric giant with 14-inch teeth, was a member of the same family. The physeteroid whales, the group containing sperm whales, have a fossil history stretching back around 23 million years. Leviathan represents an extreme branch of that family, one that evolved enormous teeth and hunted other large mammals. Modern sperm whales represent a different branch, one that evolved an enormous biosonar organ in the head called the spermaceti organ, traded active biting for stunning prey with sound, and switched primarily to hunting deep-sea squid. The sperm whale's hunting style is extraordinary. It dives to depths of around 6,000 feet, holding its breath for up to 90 minutes. At those depths, in total darkness, its sonar system produces focused clicks that bounce off giant squid and return as echoes. The whale tracks the echo, adjusts direction, accelerates, and catches squid at depths and speeds that remain partly mysterious, even to scientists who study them full-time. Sperm whales live in complex social groups led by older females who maintain knowledge of migration routes, feeding grounds, and ocean conditions accumulated over decades. The information those older females carry is so important to group survival that researchers believe the death of a matriarch causes measurable harm to the group's ability to find food for years afterward. The same social intelligence and long-term memory that Leviathan probably possessed, operating on pack-hunting dynamics in the Miocene Ocean, is carried forward in modified form by sperm whales today. The lineage did not die with Leviathan. It adapted, changed its hunting strategy, shrank its teeth, grew its brain, and found a way to survive every mass extinction and ocean change of the past 20 million years. The sperm whale today faces threats that no prehistoric predator prepared it for: ship strikes, noise pollution disrupting its sonar, reduced squid populations from warming oceans, and chemical contamination moving through the food chain. A lineage that survived Leviathan, survived Megalodon, survived the Ice Ages, is now under pressure from changes happening faster than evolution can respond. But the ocean's most extreme living example of prehistoric scale is an animal so large it makes sperm whales look modest. The blue whale is the largest animal confirmed to have ever existed on Earth. Larger than any dinosaur, larger than any prehistoric sea reptile, larger than Shastasaurus, larger than Megalodon. A full-grown female blue whale reaches around 100 feet in length and up to 350,000 pounds. The heart weighs around 400 pounds, roughly the size of a golf cart. The main blood vessel, the aorta, is wide enough for a human to crawl through, and it eats krill. Tiny shrimp-like crustaceans, each one around 2 inches long, swarming in clouds billions strong in cold, productive ocean water. The strategy is called filter feeding, and it is one of the most successful feeding strategies in ocean history. A blue whale opens its mouth, which can hold around 1,000 tons of water in one gulp, then pushes that water out through a system of bleed plates, trapping millions of krill inside. One mouthful can contain millions of calories. A blue whale eats around 4 tons of krill per day during peak feeding season. This strategy requires enormous schools of krill, which requires productive, cold, oxygen-rich water, which exists in the polar and subpolar oceans. Blue whales migrate seasonally between cold, rich feeding grounds and warmer waters for calving. Their entire annual cycle is organized around the location of krill. The blue whale grew to its current size for a reason scientists have been piecing together over the last decade. The cooling of the oceans over the last few million years concentrated krill in specific regions, creating massive, dense schools in predictable locations. Whales that could hold more water per gulp, and therefore filter more krill per mouthful, had a feeding advantage. Over millions of years, selection pushed body size upward. The biggest whale gets the most food in the fewest dives. Blue whales were hunted nearly to extinction in the 20th century. At their lowest point in the 1960s, the global population had dropped to around 300 to 400 individuals from an estimated starting population of around 200,000. Industrial whaling harpoons, explosive-tipped, fired from fast motorized ships, killed them faster than they could reproduce. The population has been recovering since the international commercial whaling ban of 1986. Current estimates range from 10,000 to 25,000 blue whales globally. Recovery is slow because blue whales reproduce slowly, giving birth to a single calf every 2 to 3 years after a 12-month pregnancy. The largest animal ever to live on Earth was nearly wiped out in the 20th century by humans with industrial tools. It is recovering now, but slowly, in an ocean that is warming, acidifying, and filling with noise that disrupts the low-frequency communication calls blue whales use to find mates across thousands of miles of open sea. The pattern is clear when you lay out the history. Ocean apex predators peaked in size during the Mesozoic, the age of sea reptiles, and again during the Miocene, the age of Megalodon and Leviathan. The animals living today, great white sharks, orcas, sperm whales, are large by human standards but modest compared to the giants that came before. Something changed. Several things, actually. Ocean temperatures are the first factor. The warm, shallow seas that covered large portions of the continents during the Cretaceous and Miocene periods provided enormous hunting grounds rich in prey. As the climate cooled over the past few million years, those warm, shallow seas retreated. Cold water dominates larger portions of the ocean now. Cold water is less immediately productive for large, warm-requiring predators. Prey size is the second factor. The largest whales of the Miocene were mid-sized species that Megalodon could efficiently target. Over the past few million years, whale evolution has produced two extreme strategies: the very large filter feeders like blue whales and the very fast-toothed hunters like dolphins and orcas. The mid-sized prey that Megalodon specialized in is less abundant now. Continental arrangement is the third factor. When the Central American Seaway closed 3 million years ago and various other geological changes reshaped ocean current patterns, nutrient-rich upwelling shifted. The productive coastal zones that concentrated prey for Megalodon and Leviathan in specific predictable locations became less reliable. The result is an ocean where being very large is less advantageous than before. Orcas succeed by being highly intelligent group hunters. Great white sharks succeed by being flexible in prey. Sperm whales succeed by diving to depths no predator can follow, and hunting squid that is nearly unlimited in supply. None of these strategies require the raw body size that Megalodon or the giant pliosaurs carried. This tells us something uncomfortable. The conditions that produce giants are not permanent. They come and go with climate, ocean chemistry, continental position, and prey availability. The ocean we have right now may not be capable of sustaining another Megalodon, even if one could somehow be recreated. The ecological scaffolding that supported it is gone. The question that follows naturally from this is whether anything comparable might still be out there in portions of the ocean that remain almost entirely unexplored. The idea appears in movies constantly. Megalodon never went extinct. It simply moved to the deep ocean, to the lightless abyss beyond human reach, surviving undetected for millions of years. It is a compelling story. It is also almost certainly wrong, for specific scientific reasons. Megalodon was a shallow water predator. The fossil evidence is explicit on this point. Teeth cluster in coastal sediments, in shallow sea deposits, near ancient shorelines. Deep ocean sediments, which accumulate very slowly and can preserve fossils over tens of millions of years, contain no Megalodon teeth younger than 3 to 4 million years ago. If Megalodon had moved to the deep ocean and survived there, some of its teeth would eventually have fallen to the deep ocean floor and been preserved. They have not been found. Megalodon's hunting strategy required prey found in surface waters. Large whales breathe air. They live near the surface. A deep ocean Megalodon would have had nothing to eat that matched its caloric needs. The deep ocean does contain large animals that remain poorly studied. The colossal squid, species of a large fish like the giant oarfish, which reaches around 35 feet. Deep sea sharks, including the Greenland shark, which grows slowly to around 23 feet and may live over 400 years. None of these approach Megalodon scale. A genuinely unknown animal the size of Megalodon living in the modern ocean would leave signatures scientists would detect. Whale carcasses with massive bite wounds consistent with a very large shark would wash ashore. No such carcasses have been documented. Living Megalodon-scale predators would need to surface occasionally, or show in the echolocation data of sperm whales hunting at depth. No such signals have been recorded. The deep ocean does hold genuine surprises. New species of fish, squid, and invertebrates are discovered every year. Large deep sea creatures remain poorly catalogued, but there is a significant difference between unknown species in the invertebrate and small fish category, and a 60-foot apex predator remaining undetected in a world where ocean monitoring technology spans satellites, deep-sea cameras, acoustic arrays, and whale-mounted biologger tags covering millions of square miles of ocean. The honest scientific position is that Megalodon went extinct 3 to 4 million years ago and has not been living in the deep ocean since. The real question is what the ocean loses when a predator that large disappears. When Megalodon vanished, it left a hole in the ocean the size of itself, and the effects cascaded through every level of the marine food web in ways scientists are only beginning to fully understand. Megalodon targeted large baleen whales, particularly the mid-sized species in the 15 to 40 foot range. Those whales are the same ones that feed on enormous quantities of krill and small fish. With Megalodon gone, the hunting pressure on those whale species disappeared. Their populations grew. Larger whale populations consumed more krill. More krill consumption affected the fish that also eat krill. The change moved downward through the food chain, altering species abundance at every level. Ecologists call this a trophic cascade. The removal of a top predator does not just affect the animals directly below it in the food chain, it affects every level all the way to the smallest organisms. The classic modern example is wolves in Yellowstone. When wolves were reintroduced to Yellowstone in the 1990s, they changed elk behaviour, which changed where elk grazed, which allowed riverbank vegetation to grow back, which changed water flow in streams, which affected fish, beavers, and songbirds. One predator, cascading effect down to stream chemistry. Megalodon's removal from the ocean would have created a trophic cascade orders of magnitude larger. Scientists found evidence of it. Around the time of Megalodon's extinction, whale body size shifted. The average size of baleen whales increased significantly. Scientists published research in 2023 showing that gigantism in baleen whales correlates with the disappearance of large shark predators. Without Megalodon hunting mid-sized whales, the selective pressure-keeping whales in the mid-size range vanished. Whales grew, culminating eventually in the blue whale. The blue whale may exist because Megalodon went extinct. The largest animal ever to live may be a direct consequence of the absence of the largest predatory fish ever to live. This relationship between predator extinction and prey evolution is a pattern that repeats across the fossil record. When a top predator disappears, the animals it hunted change over subsequent generations in ways that reflect that absence. The removal of large sharks from modern oceans through overfishing is already producing measurable changes in prey populations that scientists are watching in real time. The lesson is that no predator exists in isolation. Every giant in this list was connected to everything around it in ways that stretched across the food web. Remove the giant, and the web reshapes itself, sometimes in directions no one predicted. Imagine the modern ocean suddenly containing every predator from this list, restored to full size and full health, competing for the resources of the 21st century sea. Megalodon, Leviathan, Predator X, Mosasaurus, Basilosaurus, Anomalocaris, the whole collection, return to a world that has changed enormously since any of them were alive. Which one actually wins? The answer depends entirely on what you mean by winning, and the reasoning reveals something important about how predators succeed. Raw size and bite force favour Predator X. That 47,000 pound per square inch bite crushes anything. But Predator X was a specialised ambush predator in deep water. The modern ocean has fewer of the large ichthyosaurs and sea reptiles it evolved to hunt. Its prey base does not exist anymore. A Predator X in the modern ocean would need to redirect that crushing bite toward large whales, and it is unclear whether its hunting strategy would work effectively on fast-moving echolocating sperm whales that can detect it acoustically before it closes the distance. Leviathan has strong arguments in its favour. As a warm-blooded whale, it can thermoregulate in the modern ocean's colder average temperatures. Its intelligence rivals modern sperm whales. Its teeth can handle any prey item alive today. It would likely be able to hunt baleen whales, large sharks, and anything else in the modern ocean that fits in its mouth. The modern ocean still contains whales, Livyatan knew how to hunt whales. The match between predator and available prey is strong. Mosasaurus would struggle. It was an air breather that could not echolocate, hunting by vision in a modern ocean where its prey, large surface-swimming animals, have largely been replaced by faster, more evasive marine mammals with sophisticated senses. The most likely answer, examined honestly, is Livyatan. Warm-blooded, intelligent, socially organised, targeting prey that still exists in large quantities, capable of functioning in the temperature range of the modern ocean. If any prehistoric predator could drop into today's seas and succeed without a long adaptation period, the evidence points there. But here is the part that actually matters beyond the thought experiment. The modern ocean already contains extraordinary predators. Orcas coordinate hunts with a level of tactical intelligence that rivals any animal ever documented. Sperm whales hunt at depths no prehistoric predator reached, using biological sonar of stunning precision. Great white sharks have been perfecting their body plan for tens of millions of years. The ocean did not stop producing remarkable predators. It produced different ones, built for a different ocean, just as capable of dominating their environment as any giant from the past. The prehistoric giants were extraordinary, but so is what replaced them. The ocean has never stopped being the most competitive, most ruthless, most biologically creative environment on Earth. It never will.